Yes, I think it should be okay now. So it's a pleasure for me to introduce our next speaker, Professor Raja Aboulaich. But your slides disappeared. Raja, could you please return your slides? Yes, okay, so here are the slides, so no. Okay, so please return your slides and you can start your presentation.
Okay.
Yes, we see your slides, we hear you, so please, you can start your presentation.
Okay. Thank you very much, Vitaly, for your invitation. Good morning, everyone. In this talk, we will present the simulation of tumor growth using mathematical and agent-based modeling. This work is a part of doctoral thesis of Salma Shabbar and is developed in collaboration with Abdelrahman Habbal and from University of Nice and El Mahdi El Garmah from ERA School in Marrakesh. I will follow the next outline. After a brief introduction, I will present an optimization formulation using a PDE model and a numerical resolution with some numerical results. And I will present a hybrid model using NetLogo. As cancer is the second leading cause of this worldwide, hence the interest of scientists and in particular mathematicians in this disease. We are very interested by this problem, and I will present mathematical modeling, but only a brief introduction how we can differentiate disease cells from healthy one. The healthy cells are divided in a controlled process to ensure the proper functioning of the organs. But the abnormal cells have an excessive and anarchic division, and we have development of malignant tumor. In order to proliferate, the cells need nutrients. Insufficient nutrient supply leads to the emergence of quiescent cells. An extended period of quiescence leads to cell necrosis. The tumor tissue consists of healthy cells, proliferative one and quiescent and necrotic one. In this work, we will neglect the quiescent state, and we suppose that the only nutrient is the oxygen. The tumor growth is modeled with respect to two different levels: the cell density evolution for healthy cells, proliferative one and necrotic one, and we are looking for a geometric progression of a free boundary, which is a contour of a tumor. let omega be the tumor domain at time t. We consider the definition of rates of mitosis and necrosis as following. As the equation lambda mitosis is computed and the rates of this also depending of the concentration of the oxygen in the tissue. And we denote by C3's oxygen threshold, below which the cells are short in oxygen and become necrotic. And the oxygen is diffused through the tumor tissue and consumed by the tissue following the diffusion, the next diffusion equation. Depending especially on the density of the proliferative cells. Inside omega, which is the supposed tumor, the cells move with a velocity v, and we can write the system 2, which is the conservation law for each cell density. We have the first equation for the proliferative cells, and the second one for the necrotic one, and S is the healthy one. And we suppose that the cells are incompressible, and at every point the sum of the density is equals to 1. We assume also that the tissue has the structure of porous medium, and we use the Darcy law in order to close the system of PDE equations. And then the velocity can be computed as a gradient of the pressure, where P is the pressure in the tumor tissue, as introduced by Ambrosi and Preziosi. We can then have the expression of the pressure, which can be computed by the Laplace equation. And depending on the oxygen, the rate of mitosis of the oxygen, and the proliferative density, or density of proliferative cells. And then we obtain the PDE system with some boundary condition. But the boundary of omega is also unknown, and we have to compute it. The objective then is to simulate the shape of the tumor and to simulate the free boundary evolution. We assume that the tumor is subjected to a constant external pressure, P0, in the domain D minus the tumor omega. And then inside the omega, inside the tumor, the solution, the P is the solution of the system of PDE equations. And then we can compute the free boundary using the next cost functional, which is defined as the integral of p minus p0, because we search to have p equals to p0 on the boundary of omega. In order to avoid the instability which can be caused by the computation of the derivative of the cost functional defined on the boundary, because we have to compute the derivative as a shape derivative, and we know that this computation can cause some instability. We suppose that P is equals to P0 outside omega, but also on the boundary. And we can use the cost functional defined by the equation 4. And then we can use the shape derivative in domain and not only in the boundary. In order to compute or to simulate the evolution of the free boundary, we use the level set method. The initial location of the tumor boundary is given by psi in t equal to 0. The tumor boundary evolves over time with a normal velocity and is captured by transporting the values of the level set function psi by the velocity v. And we have to solve the transport equation using the velocity v. This velocity, we will compute it using two approaches. We use firstly, we use the Darcy law directly, and we can obtain the velocity. We can obtain the velocity as a gradient of the pressure. And this can be used in order to compute psi and to compute the free boundary. And we can also use a shape optimization method. The optimization problem is given by the minimization of the cost functional as defined before, subject where the pressure P subject to the PDE system, and we can write a Lagrangian associated with this optimization problem, and this Lagrangian permits to compute the adjoint states variables. And writing the derivative of L with respect to the states variables and writing the optimality conditions, we obtain the derivative of L with respect to the pressure, to the proliferative density and necrotic density, etc. And we can obtain the adjoint variable, which are phi n, phi p, etc. and we can compute the shape derivative of the cost function using the state variables and the adjoint variables. And then the expression given by these variables permits to compute the direction of descent in order to simulate the evolution of the free boundary. We can then obtain the next algorithm. We have to initialize the level state psi and the state variables, and then we compute, if we use the method 2 or the shape optimization method, we have to compute the adjoint variables, and then we compute the cost function and the velocity, and then we can compute, we can iterate in order to compute in each iteration the expression of G, of the cost function, and we update the level set at each iteration. Some numerical results. We have the first figures using Darcy law to compute the velocity, and the second one using a shape optimization method. We remark that the slice of tumor volume evolution for the first method, this shape optimization method takes more computational time because we have to compute the adjoint state variables and the derivative of shape functional G. We have only 70 second in CPU time for the first method and 16 for the second method. But we remark that the tumor keeps a spherical shape in the second method, in the shape optimization method. In the following, I will present a discrete method which is coupled with a PDE equation. It is a microscopic modeling. We consider a cellular level. Each cell is represented by an agent interacting with its environments and the other agents. The behavior of the agents is governed by rules derived from biology that describe the observed phenomenon. And the hybrid model is a combination of agent-based modeling, which describe the cell's behavior, and a PDE equation to describe the environments of the cells. We used NetLogo in order to simulate the agent-based system. It is a programming language and modeling environment which is free, and we can simulate all the discrete, many discrete problems. And we use also MATLAB to solve the oxygen diffusion, which is a PDE equation. We suppose that, as before, that we have three types of cells: healthy cells, proliferative one, and quiescent one. The parameters of the model are the initial number of cells, the rate of mitosis, and the probability of mutation. Then we initialize in NetLogo the tumor environment, which is omega, which is the union of the patch, a finite number of patch. We create n healthy cells, and the initial oxygen concentration to each patch, and a selection of some patch that will act as a blood vessel and supply the environment with oxygen. In NetLogo, at each time iteration, the environment is supplied with oxygen from the vascular system through the patch S, that will act as a blood vessel. And for each cell, if the mitosis condition is met, a cell identical to cell I is created. If the mutation condition is met, mutation of cell E into a cancer cell. If CK is inferior to C minimum, cell E is healthy cell, then we have death of cell E. Cancer cell, which cell becomes quiescent, or a quiescent cell where cell E death if it is quiescent, if its quiescent state exceeds the Tmax iteration. The oxygen concentration are collected from the patch and set to MATLAB as the initial condition. And we solve a diffusion equation in MATLAB using a finite difference method. The new oxygen concentration level are then sent back to NetLogo and redistributed to the patches. Some simulation results. We have in the first figure only healthy cells, some diseased cells in the second figure, and we have the evolution of the tumor. And in the last figure, we have first view of mass tumor or tumor, solid tumor. I want to show you a video if I can. I will conclude before, and I will I will try to show you the video. In this work, we considered two different methods to model growth and simulate growth of the tumor using a continued model and the hybrid one. In the hybrid one, we used agent-based model coupled with a PDE equation. We remark that a continuous model is based on abstract mathematical parameters which can be difficult to understand by the users. By combining the oxygen diffusion equation with the agent-based model, we obtain a model which is more easily assimilated by clinicians. Both developed models can be extended to take into account the effect of medical treatment of the tumor development. Some used the references. And I will try to show you the video of net logo. And we see the evolution of the cells and the constitution of the tumor. Okay, thank you. Thank you very much.
Thank you, Raja, for this very interesting presentation. Unfortunately, we don't have time now for questions and discussion. So I suggest that listeners who have questions can directly contact our speaker or send the questions to us, and then we will send to the to Raja. So I would like also to say that we have several participants here who work on agent models or hybrid models for tumor growth modeling. We just had the presentation by Kenneth before. Also, Anas Bushnita, who is among the listeners, also Angelique Stephanou, who will give just the presentation right now. So, in fact, what I suggest, we can make a separate meeting to discuss these very interesting questions. But now we have to move to our next talk. And Angelique, could you please share your screen?
Okay, can you hear me?
Okay, thank you, Vitaly. And any
Yes,
question? Any question will come by email.
Right, thank you very much. Yes, Angelique, we hear you.
Okay, so I can.
So please share your screen.
Okay, I share my screen. Okay, can you see my screen?
Just a moment. There's something happening, but not yet. Yes, now we see it. Could you please make full screen?
Okay, so this is full screen. Is it okay?
This is full screen. Okay, perfect. Thank you very much. So okay. It's a pleasure for me to introduce our next session, Angelique Stephanou from Grenoble. Angelique will tell us mathematical modeling of cancer cell metabolism. Please, Angelique, you can start your presentation.
Okay, thank you very much, Vitaly, for this invitation. It's a pleasure to talk and present these new simulations. So I will talk about mathematical modeling of cancer cell metabolism. And so why cancer and metabolism? So there is a clear increased interest for tumor cell metabolism over the last 10 years. So we can see that through the development of, there are lots of conferences organized on this particular subject. So very recently, there was two very nice conferences this year about these questions. So why is it so interesting now? It's because mostly cancer is seen more and more seen as a metabolic disease, and this has some implications about the repurposing of drugs that can target directly the metabolism, and this is actively considered as an anti-cancer strategy. So we have the example of metformin, because for patients suffering from diabetes, we discovered that they were, when they had a tumor, the tumor was regressing, and this was mainly because of the intake of metformin that was regulating the glycolysis for these patients. And so it was an interesting thing to notice and to put forward in research. So the main point is how to control the metabolism, and of course, using mathematical modeling is a good way to start. So just to present what I want to, what is the metabolism I'm considering in our simulation. So metabolism is an extremely complex questions. So in my case, I will just focus on the relationship between two metabolic modes, which are the oxidative phosphorylations and the glycolysis. So the oxidative phosphorylation is the consumption of oxygen by the cells to produce ATP. So typically, when there is enough oxygen for the cells located at the neighborhood of blood vessels, they can have access to oxygen, and so they can burn this oxygen to produce their ATP. And as we move away from the blood vessel, then we observe a gradient of oxygen, and this gradient of oxygen will lead at some points to hypoxia, and then we can observe the metabolic switch that the cell will rather use glucose instead of oxygen to produce their ATP. So, and this process, the glycolysis, is producing a lot of acidity around the tumor. And as we will see, acidity has a lot of implication for tumor development. Okay, so in the case of tumor, what we observed is a particular effect about the tumor cell in the way they modify their metabolism. So in a differentiated tissue, what we observe is that in presence of oxygen, then we have the oxidative phosphorylation using the mitochondria. And when oxygen is lacking, then we have this switch to glycolysis, and with the production of ATP through this process. And what we see is that the production through glycolysis, it's much less effective in terms of quantity, because we just produce 2 mole of ATP for 1 mole of glucose. However, it's a very fast process, so it might have some interest because it can produce a lot of ATP in a very short time, rather than the oxidative phosphorylation, which is a very slow reaction. And this is exactly why perhaps that's the reason why the tumor cells tend to favor whatever the level of oxygen in the environment, to favor the production of the glycolysis and to produce its ATP. And the consequence of this is that we have always around the tumor a high level of lactate and acidity. And so this is the main part that is favored by the tumor cell. So I present this here because we will see that at the end of our simulation, we will have some conclusion about this Warburg effect. Okay. So my presentation will have 3 main points. So I will first focus on the role specifically on the role of acidity and the consequence for optimizing pH-dependent drugs. Then I will present a very simple model of cell metabolism, which is just based on the impact of acidity. And then I will present a more comprehensive model that integrates more aspect of metabolism. And the aim is to investigate the relationship between the tumor microenvironment and the cell adaptations and fate. So first, about the role of acidity in the functioning of drugs. So we focus on the case of temozolomide. So this drug is a cornerstone molecule which is used against glioblastoma. And it's why this drug in particular, it's because it's one of the only drugs that is able to cross the hematoencephalic barrier. So it is usually associated with radiotherapy, and it's for a lifetime increase of only a few months. So it cannot cure cancer, but just delay the outcome. So the TMZ, the temozolomide, is an alkylating agent that tends to form DNA adducts that are responsible for the cytotoxic damage inside the tumor cells that will ultimately result in cell apoptosis. So we specifically investigated this drug because its activation is pH dependent. So it's a work that has been made in collaboration with Annabelle Balesta. And we wrote a paper with what the aim was to investigate how acidity can be a potential therapeutic target to improve the efficacy of this drug. So the temozolomide, as I said, is pH dependent. So it's a very complex way to transform into its active form. So the TMZ transforms in 2 steps into a cation, and the cation is the active molecules against the tumor. So in the first stage, it transforms into an empty compound, and this dependency with the pH is as follows. So when the pH is very acidic, the transformation cannot take place. We need to have a physiological pH for this transformation to occur. And in the second step, it's completely the opposite. The empty can transform into the lethal cation just when the pH is acidic, and when it's physiologic above 7, then the transformation cannot take place. So we have this phasic transformations with 2 different levels of pH acidity in the environment required to obtain this cation that can kill and produce the adduct on the tumor cells. So we developed a very simple models, and we consider two compartments in the model: the extracellular compartment and the intracellular compartment. And for a start, we will just consider what happens inside the cell. So we will completely neglect all the reactions outside the cell to focus on what's happening inside the cells. So the eye in front of every species is to mention the fact that it's intracellular reaction. So it's a very simple model. We take into account the TMZ, the MTIC, the cation, and the production of adducts. And we have this kinetic reaction in each case. And we observe that we can find our kinetic reaction that depends on acidity. So the main point is to be able to evaluate the intracellular pH to know how this reaction will, with which speed this reaction will take place. So it's a complicated questions, because when we looked at the literature, we were very surprised to discover that there are very few studies that can track back the relationship between the intracellular pH in connection to the extracellular pH. So what we did, it's a review of the literature to try to connect these 2 conditions, how the intracellular pH is regulated regarding the extracellular one. So we found very different studies on lots of different kind of tumor cells. So each symbol on this curve represents a different type of tumor. So we've been able to reconstruct this line, this function. It's a linear function, which is interesting in a sense. And so we've been able, using this line, to predict what can be the intracellular pH for a tumor cell given the extracellular pH. In comparison, we see that for the normal cells, the pH is not able to adapt, and it is following roughly the external level. So there's no capacity of adaptation. The capacity of adaptation for a normal cell is very weak, and so it just follows the values of the extracellular pH. And basically, normal cells, when the pH is below 7, is not able to survive and usually die. So we run the simulation with the previous models with one function that concerns the tumor cells. That's the result we obtained here. And one with the result we obtain with normal cells, which are here. So for the tumor cell, we observe that we can generate lots of adducts, which means damage on the DNA when the pH is acidic. So the optimum is here around 6.6. And for the normal cells, in fact, there are very little damage that are made on the normal cells, because usually they die when the pH is very acidic. And here we see that at the opposite, it's rather the physiological level, which is more lethal than the acidic level. So if we want to implement this therapy into test this therapy on a patient, the aim is to have the maximum effect on the tumor cells and the minimal effect on the normal cells. So we we plot the two results on a 3D graph with the one data, which is the time of exposure. And we see that this is the red curve is for the tumor effect, which needs to be maximum, and the effect on the normal cell needs to be as minimum as possible. So we have these two curves, and if we make the difference in between these two curves, we obtain these 3D curves, and this gives us the heat map where we can have the maximum impact of the drug and the minimum impact on normal cells, and the optimum pH for the summit of the curve is around 6.8 and 7.5. So this is very theoretical, and then in the next step, we will need to test this with real data, patient data. So to be able to interpret this data, we thought it would be interesting to have some knowledge, some more knowledge on how it works, this pH regulation. So we decided to propose a simple model of cell metabolism, and to really specifically focus on the impact of the extracellular acidity on this metabolism. So to construct the model, we based ourselves on some basic observations made that are very well-known phenomena. So first, the glucose uptake increase with glucose availability, which is completely normal. The same for oxygen, the same for lactate. As much when there's lactate with we have an increase with lactic acidosis. So we also observed, which is completely natural with the metabolic switch, that when glucose tends to be liking, then oxygen level will increase. And one particular point that we wanted to implement in our model is the effect that the glucose uptake decreases drastically in presence of acidity. And this has been observed in many different cell lines. So we thought it would be a very interesting hypothesis to test. And so we implemented this specifically in our model to test the impact of this acidity. And another point is that the fact that pyruvate concentration remained almost constant through the pH variations. So this is basically based on these two studies, and one which is rather old now, it's 1992. So this is the model that was proposed at the time. And in this model, we just added the acidity, the impact of acidity on the metabolism. So acidity is inhibiting the glycolysis. So this is what we see here. The uptakes are presented in two different conditions for a physiological pH and an acidic pH. And what we see is that the uptake of glucose weakly depend on the amount of oxygen present. The same for oxygen, except when the level of glucose is very, very low. In that case, the oxygen will take over. And what we see is under acidic condition with the inhibition implementation, we have a complete inhibition of uptake of glucose under acidic condition. And the oxygen uptake does not depend at all on glucose. Okay. So this is just to show you the form of the different uptake rates. So we see here the glucose uptake rate that depends on the pH, on the acidity. On the other hand, the uptake of oxygen is made in a way so as to maintain a constant level of ATP production. So the level will regulate the uptake of oxygen so that the ATP remain almost constant in the cell, as long as it is possible given the environmental constant elements. And also the lactate in the model that is also strongly pH dependent. So what we observed is the production of ATP in the different conditions. So ATP level is higher when both oxygen and glucose are available, of course. So this is under physiological conditions. And oxygen appears as the first limiting substrate, since glucose alone cannot maintain sufficient amount of ATP to sustain proliferation. And under acidic condition, since the glucose is inhibited, oxygen alone dictates the amount of ATP that can be produced. So it's what we see here. So as an example, we put the states of the cells that can be associated with the level of ATP. And typically, when there's not enough ATP, then the cell is not able to maintain its metabolism, so it tends to become necrotic. And when there is sufficient amount of ATP, then the cell is quiescent. And when there is a lot of ATP, and the cell can function normally and is able to proliferate. So the results I just shown here are just based on one single cell. And of course, we'd like to have the full picture. So we consider this as a simple model into each cells, and we produce some simulation using an agent-based model. So yes, so the software we used is not NetLogo as previously, but is a PhysiCell, which is also a free software that can be found on GitHub. So it has been developed by Paul Macklin in Indiana State, and it's freely available, so we can use it, and it's very well documented. So it's a very nice software to use to run some growth, some 3D growth of tumors. So we can take into account a lot of a huge amount of cells, up to thousands of cells. So it's and it's very easy to develop, to work. So we have a grid. The grid is a regular grid that allows to compute the diffusion of the different elements of the simulations. And the position of the cell is lattice free. So we can take into account the fact that the cell can be, we have a various level of density of cells in the cellular automaton, in the agent-based model. So in the center, it's much more dense than in the periphery, for example. And the cells are not all with the same diameter. They can vary in diameter. Okay. So we made the simulation starting with the following conditions. So what we see is that if we take an initial condition where lactate is a low, it is related to a low pH. Lactate is high, sorry, we have a low pH, and it means also that oxygen is lacking and the glucose is lacking at the center of the tumor. So the white line represents the tumor boundary. And this is a simulation we observed on the spheroids. So in this case, we did not draw the spheroid, but we started with already a big spheroid, and then we implemented the ODEs, the ODE model of metabolism, to see how the metabolism take place inside this gradient of oxygen and glucose. So we observed the gradient as expected. Nothing surprising about this. And one point is that the ATP is kept relatively constant, since it is the aim of oxygen to maintain this ATP constant here in this picture. And one interesting fact is this one. It's we observed during running the simulations that we have a layer, an annulus of lactate production. And that emerged spontaneously at the intersection between the glycolysis that takes place in the center of the tumor and the proliferation that takes place, oxidative phosphorylation that takes place at the outer layer of the tumor cells. So at the intersection of these two metabolic modes, we observe this ring. So it can be interpreted from these simulations, but we thought it was an interesting signature, in fact, of the metabolism inside the tumor cell. Okay, so then we were satisfied with this very simple model, because it gives already some insights on the way the metabolism is functioning inside a spheroid. But we wanted to incorporate more complicated events so that we can use it, for example, to test some drugs. So we needed to to develop this more comprehensive model. So as a first step, we did a review of the literature. And we found a perfect model in this literature. So it's a team of Chinese people, Li and Wang, and they developed a very nice model that already incorporate many different aspects. So it is based again on the competition between the oxidative phosphorylation and the glycolysis, but it also implements all the regulatory network at the genetic scale. And if we play on this different element, for example, we can generate a mutation, then we can observe some variation in the metabolic landscape and the consequence it can have on switching from one mode, the facility to switch from one mode to another. So this is more or less what is inside the model. So we have different aspects in it. To make it simple, we have a module which regulates the glycolysis, the fermentation, one module for the oxidative phosphorylation, and all this gene and regulation network. And in this picture, they just modified the action of two enzymes, PDH and LDH. So why these two? It's because they are just located here at the intersection between the two metabolic modes. So it permits to pass through different level of states of metabolisms that goes from proliferation to metastatic, which is highly proliferative, to normal cells. And we can explore the landscape, the metabolic landscape, just playing on these two enzymes. So we thought it's a very interesting models, but it's not perfect for the application we want to use. So we first started to modify a bit this model by adding the pH regulations. As we observed that acidity plays a role on glycolysis, then we implemented a new module that takes into account this particular effect. And also, since we wanted to run simulation in a cellular automaton and an agent-based model, we needed to add some flux between in and out flux into the cells that were missing in the original model. So we added these two modules in the models, and then we rerun some simulations using these models. And we were very happy to find that we were able to found the exact same results that we had with our very simple model, which is the appearance of this lactate ring inside the cell. And again, which is at the intersection of the proliferating cells at the periphery and the glycolytic cells at the center. And again, this layer was appearing. So it's reassuring in a way that the very simple model was already captured to capture this particularity of emergence in the growth of spheroids. Okay. So the next steps was to run much more complicated simulation, because what I didn't say here is that we started again from already grown spheroids, and we did that. The main reason is because the time for computing is very high when we have a high number of cells. So we started with an already grown spheroid, which is a way to gain some time. But we wanted to have the truth of the growth effect. And when we start from one single cell dividing and creating its own space, then we obtain this kind of results. And we immediately see that there is a big difference in terms of heterogeneities, because there are some islands of proliferations that occur in the cell, some necrotic parts that appears, and all that depends on, because it's a stochastic model in terms of uptake, and so that's why we obtain these tumor heterogeneities. And this is in complete agreement with what we can observe on experimentally if we use pathological data on spheroids. So we can have in this map lots of information of all the metabolic mode of the tumor cells, and also lots of information on the cell cycle, for example. So here, for example, we can spot the location where we have a specific phase of the cycle, and so on. Okay, so one key results. So I was talking about the Barbour effect at the beginning of the talk, and it's considered as a hallmark of cancer. And our simulation shows that, in fact, it might be due to the dysregulated condition of the environment rather than an intrinsic property of the tumor cell. And why that is, first, because the Barbour effect is observed on normal cells, so it is more and more documented in the literature. And also our simulations show that it's a context-dependent effect, since we can see the Barbour metabolism appear in the simulations, and then when the conditions are changing around the cell, specifically when the level of acidity tends to rise, then this effect disappears. So it's a reversible effect and strongly depending on the environmental condition. Okay. So the main point of all this work is at the end to have a tool to try to predict the effect of medication and to apply it to each specific patient. So the idea would be to take some biopsies on patients and then to use these cells to analyze them through tumor spheroids to derive the pH extracellular and pH intracellular relationship. So when we have this signature for each patient-derived cell lines, then we can use our model to identify the optimum pH with mathematical modeling, and then validate this on spheroids and also on animal models or organoids. And then we can predict the optimum therapy that can be used on one specific cell line of patients. So that's the future, that's what we aim to do. So we started in that directions and made a proof of concept. So the proof of concept was made using two very well-known cell lines that are widely used in laboratories. So we use the murine cell line F98 and U87. And why we choose these two in particular, it's first because they behave in very different ways. The growth is different. Also the appearance of the tumor is different. The U87 are very spherical, whereas the F98 have different shapes, and the level of connection in between the cell is less important in this type of tumor. So since they behave differently, we thought it would be a good example to show that it's very cell line depending. So what we did is that we took the cells of these two different cell lines and we put them in different acidic environments, and we observed how they adapt to the intracellular pH. So what we observe is that after 1 hour, they are not able to change their pH. So they just take the intracellular pH become exactly the same as the extracellular pH. And after some time, after 2, 3, 4 hours, they slowly adapt their intracellular pH. And what we observed is that the F98 cells are not able to adapt so much their intracellular pH, so they remain acidic cells, remain very acidic, and so on. Whereas in the U87, what we observe is that the cells are really able to regulate their internal acidity and to export, to secrete the protons outside the cytoplasm, and so they can rise their intracellular pH and they can survive much more easily than the F98 tumor cells. So it's interesting because they just have two different ways of managing the acidity. So this is exactly the same result here. So what we see is the level of pH extracellular equal pH intracellular with this line. And then the black dotted line shows the asymptotic state of acidity regulation. And here we see that the F98 are not able to regulate the acidic pH. They can regulate the basic pH, but not the acidic. And here in the other hand, the U87 can regulate and rise their intracellular pH by exporting the protons, and they can also do that, uptake some protons when the outside extracellular pH is too basic. So, okay. And then the next step was to test the temozolomide on these two cell lines. And as expected by the preliminary results, is that we don't find the same values for the optimum value for the concentration of for the pH that functions for the TMZ. So the F98, the optimum is rather located around 6.8, and it works better if it's more acidic for the U87. So the interesting thing to note is that the optimum pH really depends on the cell line. Okay. So I think I will stop here, and I will acknowledge my co-workers. So my PhD student, Pierre-Jacques, Kevin Swinichi, Ala Tafek, and the people with whom we did some experiments, and also some collaborators in Swansea University, Jibin Poatil, and of course Annabelle Balesta, with whom we worked on TMZ, which is a specialty. So thank you for your attention, and yes, I'm pleased to answer any questions.
Thank you very much, Angelique, for this very interesting presentation. We don't have too much time to discuss now, but I hope we'll have other occasions. But could you please shortly summarize? So when you take this pH into account in tumor growth, so finally, to make it simple, will it increase or decrease tumor growth considered with the model? I'm talking about the models, not about experiments, if you don't take into account acidity. So again, with acidity, without acidity, how it influences tumor growth in the model?
We did not really compare the modification of the growth speed, for example. What we really compare is the difference in between the metabolic mode that we can obtain. And if we don't take into account the acidity, then the tumor is behaving like as expected by what we found in the classic literature, which means that there's a Warburg effect, which is dominant in these tumors. And if we take into account the acidity, then we observe that it's a reversible effect. And there are more and more experiments now that this effect has been highlighted. There are more and more experiments that used acidity to verify if, in fact, the Warburg effect is indeed reversible. And this has very high implications, because all the treatments are based on the fact that the tumor cells are different from normal cells, that they have a very different phenotype, and this is this phenotype that we have to target. But we observe that if we don't take this into account, then we can kill as much normal cells as tumor cells. So it's important to note that finally metabolism is not that different for tumor cells. It can be it's really depending on the context, and the context can touch as much as a tumor cell as a normal cells. So this is the main point of what acidity reveals by taking it into account in these models.
Okay, thank you very much for this explanation and for this very nice talk. So at this point, we have to finish our discussion and our session, and I would like to thank again all speakers and all participants. And I also recall that we have 1 hour break now, and after that we'll have another plenary talk by Professor Tsaturyan about structural biology of muscle contraction, and another session on cardiac modeling. So you are very welcome to come back in 1 hour, and we have a break now. Thank you very much.